we are going to study about the topic called envelogram. So this envelogram, it is mainly used for analyzing the PCG signal. PCG means phonocardiogram signal. For analyzing the PCG signal, we are going to study this envelogram. So you know the PCG signal, it is a study of electrical activity, that is the sound of the heart. Okay, that is PCG signal. So now in the PCG signal, we have four heart sounds. First heart sound, second heart sound, third and fourth. First two heart sound only it is audible. Remaining two heart sounds are not at all audible. So in that case, we have to extract the envelope of the heart sound, first two heart sound. So in that case, we are going to use this envelogram. So here, to estimate the envelogram, we are defining an analytical signal which is called as y of t. So this y of t, it is formed by it's a combination of a PCG signal which is denoted as x of t here and a Hilbert transform signal which is expressed as x h of t. So we are going to take the PCG signal and apply the Hilbert transform to the PCG signal and get x h of t. So these two signals we are going to add it. So the combination of PCG and its Hilbert transform, this gives you the analytical signal. Okay. So now this signal only we are going to analyze. This analytical function, it is the complex function of time. So that is having a Fourier transform. So the Hilbert transform we can define here as xh of t is nothing but we are going to apply the Hilbert transform to the PCG signal. So when you take the Hilbert transform, it is summation integral over minus infinity to infinity x of tau divided by pi of t minus tau d tau. That is the Hilbert transform. And when you take the 1 by pi t, Fourier transform of 1 by pi t, so that is minus j signum of omega. So what is that 1 by pi t? Because the Hilbert transform of the signal, it is defined as convolution of the signal with 1 by pi t. So that's why. So here again the signum function it is defined here as minus 1 for omega less than 0, 0 for omega equal to 0, 1 for omega greater than 0. So when you analyze the same PCG signal in terms of Fourier transform domain, we have y of omega equal to x of omega of 1 plus signum of omega because we are analyzing the Hilbert transform signal in terms of Fourier domain. So that's why we have got 1 plus signum of omega. So we have that analytical signal now. So the procedure for obtaining the envelogram is first we have to compute the discrete Fourier transform for the PCG signal. Then we have to set the negative frequencies to 0. So that means we are going to define the x of k as 0 for the limits varies between n by 2 plus 2 to n. With the DFT it is defined with the index k varies between 1 to n. And then after setting the negative frequency to 0, we have to multiply the positive frequency term. So that is x of k for k varies between 2 to n by 2 plus 1. So for that particular range, we have to multiply by a 2, the DC term, and x of 1 will remain unchanged. So after multiplying with the positive frequency term, then we have to compute the inverse discrete Fourier transform of the result. Then magnitude of that result will give you the envelope of the envelogram estimate. So this is the procedure involved in computing the envelogram of the signal. And if you see the signal, you can able to see that first one represents the PCG signal in which the first two heart sounds and the third and fourth heart sounds also it is very third and fourth heart sound is very less in amplitude compared to the first two heart sounds. So here we are going to apply the envelogram and obtain the signal in terms of a frequency domain. Then we are going to average the envelogram because for multiple cycles we are going to apply the envelogram and obtain the average envelogram. And finally we are going to obtain the average envelope. The last signal represents the average envelope. So this is the PCG signal for a normal subject whose age is 23 years old. For them, we are extracting the envelogram of a signal and by averaging the envelogram over 16 cardiac cycles. Okay, so the PCG signal started here with S1. So we are applying the segmentation of the signal and then we are extracting the envelogram of the signal. Okay, so this is the reference book you can refer for this particular topic.